Okay, we are back. To continue, in the previous session, we discussed, we went through the characteristics for road users and for vehicles. Now we're going to shift gears and start talking about the traffic stream characteristics because it's one of the major elements for the traffic system. So we need to understand what are the characteristics of this traffic stream. So we mentioned earlier that we have two types of traffic streams. We have the uninterrupted traffic stream and the interrupted traffic stream. The uninterrupted traffic stream, that's basically a stream where all the accessibility for this stream is a limited access. Okay, it's either by a ramp to get into that stream, or to get off that stream, you get it from an off-ramp. On-ramp or off-ramp, that's accessibility to that stream. There is no interruption for the flow by a traffic sign or stop sign or any of that. The only interruption that might take place is due to traffic congestion. Okay, so the interruption is not exogenous to the traffic stream. It's endogenous to the traffic stream if there's any interruption. On the other hand, when we talk about interrupted traffic facilities, we are talking about, just any road, any street that there's a stop sign, there's a roundabout, there is a pedestrian crossing, there is a traffic light. These are interrupted, and the interruption, it's by design. There is an interruption in the structure of that road or that facility. So what are the main parameters? For traffic streams, we have two set of parameters. We have macroscopic parameters and the microscopic parameters. The macroscopic, okay, these are collective parameters, okay, these are the volume or flow rate, the speed of the stream, the density of the stream. So the volume, that's a macroscopic parameter, and the average speed for the stream and the average density or the density of the stream. These are macroscopic. On the other hand, we have the microscopic. These are miniature, or that's on an individual vehicle basis. We have the vehicle headway, the spacing, and the speed of individual vehicles. Let's start with the traffic volume or flow rate. We might refer it to both. So the traffic volume or flow rate is defined as the number of vehicles passing a point on a highway or a given lane or direction of a highway during a specified time interval. Usually the units are vehicle per time. This is traffic volume or flow rate. The time is either hour or day, week, or year even. We have traffic volume, for example, we have the average annual daily traffic volume. We have the average, we discussed all of this before, the average annual weekday traffic, okay? And we have the average daily traffic volume, the average weekday, okay? We're not gonna elaborate on that, we have discussed it before. The typical use for the daily volumes, the daily volumes are used primarily for network planning, design, feasibility assessment, prioritization of maintenance, assessment of current demand. It's not used for design, okay? Why? This is an example for calculating the average annual daily traffic volume. And why we don't use the traffic volumes, okay, the average daily traffic or the daily traffic volume, why we don't use it for design purposes, okay? Because these volumes vary significantly over the 24 hours. The traffic volume over the one day, okay, it varies from hour to hour, okay? That's why we don't use the daily traffic volume for design. Instead, we use the directional design hourly volume. The directional design hourly volume is basically derived from the average annual daily traffic volume, okay, by multiplying this into the K and D. K is basically the proportion of traffic volume occurring during peak hour. D, that's the directional proportion or the directional split, okay? And the K and D are based on the location and type of the facility. So if we are talking about a rural facility, the K is usually in the range of 15% to 25%. And the split factor D is 65% to 80%. If it's suburban, the K factor, it gets reduced slightly to be 12% to 15%, and the D factor 55% to 65%. By the way, these values are based on US data. So here we are in Saudi Arabia. If we want to use these factors, we need to have to come up with our own factors, okay? And usually this is derived by, a subject matter expert or someone expert of the location of this facility. Okay. That's an explanation for the K. So that's basically the proportion of the daily volume that occurs during the peak hour. Okay. And the D, that's the percentage in which in the peak direction. Then there's another issue, which is the peak hour factor. What is the peak hour factor? The peak hour factor is basically how we can estimate. Okay, first of all, what's the definition of peak hour? Peak hour is basically the single hour of the day that has the highest volume. Okay, so that's the peak hour. How can we estimate the peak hour factor? Basically, we count the volume during the peak hour period, okay, in a 15 minutes intervals. Then we pick the consecutive four 15-minute intervals, and this is going to be the peak hour. Then within that 4 15 minutes, we pick the highest or the maximum 15 minutes, okay, volume, and we divide the peak hour volume by 4 by the peak 15 minutes, and that's how we get the peak hour factor. That was an example, okay, on how we calculate the peak hour factor, and we identified here that's the peak hour from 7:15 to 8:15, and you have this in the previous recordings. You can refer to it. We are not going to elaborate. The second parameter, which is the traffic stream speed. We have two types of speed. We have the time mean speed and the space mean speed. What do we mean with the time mean speed? Basically, the average speed of all vehicles passing a point on a highway or lane over some specified time period. The space mean speed is basically the average time of all vehicles occupying a given section of a highway or lane over some specified time period. Okay, so which one is more accurate? The space mean speed is more representative. The time mean speed is usually higher than the space mean speed. Why? Because the time mean speed gives advantage to the speeding vehicles, so they appear more frequently in the sample. And we had an example here, and we showed that the time mean speed is 61.61, and the space mean speed was lower than the time mean speed. And the reason for that is that the SMS takes into account the time vehicles occupy. Okay. Traffic density. What's the definition of traffic density? Traffic density is defined as the number of vehicles occupying a given length of a highway or lane, generally expressed as vehicles per kilometers or vehicles per kilometers per lane. Okay. Density is usually difficult to be directly measured. It's problematic for direct measurements. You need to have an aerial photo, for example, to calculate the traffic density. But we rely on another parameter, which is the occupancy. What is the occupancy? Usually, if we have a loop detectors, as we have here, okay, so it's basically the occupancy will be the percentage of time defined as the amount of time a specific part of the traffic stream is occupied or covered with a vehicle. So in this case, that's the loop detector. The percentage of time this loop detector is covered with a vehicle, okay, we calculate it from here. That's basically, we calculate the density from here, because basically occupancy is sigma T1 over T. Then the density will be 1000 multiply the occupancy divided by vehicle length plus the loop detector length. Any questions? Okay, let's move on. So now we are done with the macroscopic speed. We go to the microscopic parameters. We are done with the macroscopic parameters. Now we go to the microscopic parameters. The first parameter is spacing. Spacing is defined as the distance between successive vehicles in a traffic lane measured from some common reference point, such as a front bumper or front axle, okay? And the density, if we have this, then the density become 1000 divided by the spacing, okay? Headway. Headway is defined as the time interval between successive vehicles as they pass a point along the lane, okay? So basically, if you are standing on a highway and you are counting each time a vehicle passes you, you are measuring the time between the vehicles. That's the time headway, okay? So from that, if we divide, if the headway is measured in seconds, then the flow rate will be 3,600 seconds divided by the headway, because we have 3,600, we have 3,600 seconds in 1 hour. So if we divide the 1 hour by the headway, we get the flow rate. The average speed would be the flow rate divided by the density, okay? As we can see here, that's the relationships between flow rate, speed, and density. So these models were developed early last century by Greenshield in 1934, and he assumed a linear relationship. He said that if there is no traffic, okay, and just one vehicle driving, it will drive at a free flow speed. Then the more density we have, okay, the traffic stream will start slowing down until we get to the jam density. The jam density, that's where the traffic stream becomes like almost a parking lot, okay? So that was a linear relationship. So his assumption was that the speed is inversely proportional to the density. The more density we have, the lower speed we have, until we get to the point where the speed is zero. That's jam density. Greenberg model in 1959, he assumed a logarithmic curve, and Underwood in 1961, he assumed a negative exponent relationship. Then the flow rate, that's a relationship between flow rate and density. As we can see, once the density is low, okay, the flow rate can increase, it keeps increasing until it gets to the point, to the capacity or the saturation flow rate, okay? Beyond this point, okay, the flow becomes a congested flow, okay, and the density increase, but the throughput for the traffic facility decreases, and the flow rate decrease. So it follows this parabolic curve. And next semester, inshallah, we will discuss it in more details. Then the relation between speed and flow rate. As you can see, when the flow rate is almost zero, the speed is at maximum, okay? It's at free flow speed. When the flow rate increase, the speed start decreasing. Then as the flow rate start, decreasing, that goes into the congested flow condition. That's where the speed also continue to decrease until it reaches zero. Okay, now we are done with the traffic stream characteristics. So as we started talking about the characteristics for the traffic, for the components of the traffic system. We started talking about, we discussed the characteristics for road users. We discussed the characteristics for vehicles. We discussed the characteristics for traffic streams. Now we are going to explain what are the traffic control devices. That's the fourth element of the traffic system. So what are the traffic control devices? Traffic control devices can be divided into three major categories. Traffic marking, these are the pavement marking, traffic signs, okay, and traffic signals. We have the manual on uniform traffic control devices, okay. This manual basically dictates how we, all these three categories, okay, and explains how we can use them. First of all, what's the purpose of the traffic control devices? That's defined by the MUTCD. The definition is to promote highway safety and efficiency by providing for orderly movement of all road users on street and highways throughout the nation. That's the purpose of the MUTCD. Okay, how can the MUTCD, achieve that? It defined 5 requirements for traffic control devices in order for this device to be effective in fulfilling that mission. 1, the control device should fulfill a need. It should not be redundant. Okay, that's number 1. Number 2, it must command attention of the road users. 3, it must convey a clear and simple message. It should not be confusing to the drivers. 4th, it should command respect of road users. 5, it should give adequate time for proper response. For example, you cannot put a sign for on a highway or a freeway that the exit from this ramp just 10 meters before the exit. You need to give the driver a proper distance, okay, ahead of time, okay, that the driver can make a decision on what to do. Okay, what are the content of, or the core contents for the MUTCD? Okay, the core contents for MUTCD detail the standards for the physical design and detail the standards for guidelines on where the devices should be placed, and the warrants. What are the warrants? These are the conditions that justify the use of particular device. Again, the core contents of the MUTCD detail the standards for the physical design of the device, size, color, then the detailed standards for the placement of the device and the warrants for using and guidelines for using these devices. For example, here we have a yield sign. So that's a detailed standard. It gives you the size. We have 3 sizes here, and the font and the size. This one is not detailed actually. I have other drawings that will give you the radius for everything, and all the details. You will find it in the MUTCD for these signs. Then the second component details the standards on guidelines on where the devices should be located. For example, a stop sign must be located on 12 feet minimum from the shoulder, okay, and at least 5 foot the height, okay, and all these details are for different locations. So that's for rural area, that's for residential area, and so on. Okay, then the third component are the warrants. The warrants for each device, you will see guidelines and warrants. Okay, first it starts with, for example, that's a stop control warrants. Okay, the guidance, it gives you a guidance. At intersection where a full stop is not necessarily at all times, consideration should first be given to using less restrictive measures such as yield sign. That's the guidance, that's the advice. you get. Then the use of stop sign on the minor street approaches should be considered if engineering judgment indicates that a stop is always required because of one or more. These are the warrants. So at least here say one or more of the following conditions fulfilled. Okay. So for example, you have here vehicle traffic volumes on the throughput Kaza, restricted view, okay, exists. That's what we do with the side distance triangle check, okay. And here, this one is key. This one is vital. And if the two are fulfilled, but there is a crash record, then we must put, you know, stop sign. So now we're gonna, you know, discuss the different, the three categories, the traffic signs. What are the types of traffic signs? We have regulatory signs, okay? We have warning signs, we have guide signs. What is the purpose of the regulatory signs? These are law. If you violate the regulatory sign, you get a citation, okay? Because basically these, for example, say speed limit 50 miles per hour, for example. So you must fulfill this number. If you violate this sign, then you are in trouble. You get, this is part of the law, okay? That's an enforcement. Okay, here it's a through only or left turn only. If you violate this sign, you are making a violation. Okay, so you are ought to get a citation. These are warning signs. These are just, you know, warning to give a driver the alertness that there is an upcoming hazard, okay, and he must be taking care, you know, care while, you know, making these turns or, you know, this kind of maneuvers. That's an example, for example, that you have, you know, a traffic light ahead of, you have a yield sign ahead of you, and so on. These are guide signs. These just to give you an information. It help you, you know, in your navigation on the highway. Okay, those were the three categories of signs. Now with the pavement marking, we have three types of pavement marking. We have longitudinal markings, we have transverse markings, we have object markers or delineators. So these are the longitudinal markings. Lane separators, for example, okay, is defined in the MUTCD, and these are samples of the longitudinal markings, okay. Transverse markings, okay. These basically to give you an idea that there's a yield sign ahead of time, you know, ahead of you. That's the line for pedestrian crossing, okay. If you have a yield line, if you have a sign that say yield, that's the yield line. You must yield at this point, okay. And that's a pedestrian crossing, so there is a 20 to 50 feet distance between both. The pedestrian crossing, for example, these are considered as transverse markings. Parking spaces, these are transverse markings. Lane channelization or lane designation, okay, standard arrows, these are transverse markings also as well. Also markings for speed humps, okay. This one roundabout, it includes several pavement marking. It includes longitudinal, okay, and transverse. So that's an example for the deployment of these pavement markings. Then the third part with the traffic, warrants, okay, or the traffic signals. So the traffic signals, you know, they have 9 warrants in order to deployed. Okay, and we will discuss that in the last chapter of this course. So far we discussed the main elements of the traffic system: road users, vehicles, okay, traffic stream, and control devices. Now we are going to shift into the applications. But before shifting to the application, we need to have some basic review for statistics. Okay, what do we mean with statistics? Statistics basically the art of abstracting real world via sampling and deriving general estimates that describe the real world at a certain degree of confidence. بمعنى يا شباب الإحصاء، علم الإحصاء هو علم اختزال الواقع عن طريق samples، اوكي، وبناخد من السامبلز دي measures أو مقاييس نحكم بيها على الريل وورلد. Okay, what do we need, or when do we need statistics? When we cannot measure all the data, and that's the case in traffic systems. We cannot measure all the speeds all the time for the vehicles, but we have to sample speed, for example. Okay, so how can we do that? We need to have, first of all, the sample size, because it determines how many the measurements are sufficient. Okay, what confidence do we have in the results? Okay, what is the statistical model to use? These are questions, but that we need to understand before starting doing our statistics or sampling. First of all, we do sample reduction, okay, and visualization for the measurements. We do this by the histogram for the data, collected data, and the cumulative frequency. And we have done this before online using Excel, okay? And there's measures, first, the common statistical estimators. We have measures of central tendencies. We have the mean, median, and mode, okay? In Excel, we can calculate this by having the average and the median and the mode also. Then we have the measures of dispersion, which is basically the variance and the standard deviation. These are the major measures of dispersion. Also, we have the coefficient of variation, which is basically the ratio between the standard deviation and the mean of the sample. And there's the skewness, okay, that reflects the symmetry of the data. And we had this, okay. These are some functions, how to get the mean, the mode, the median from using Excel, Microsoft Excel functions. And okay, then we go to the distributions. We have normal distribution, or the Gaussian distribution, or the bell curve, okay? The Gaussian distribution is basically assumes that everything in life according to random distribution, okay, and the normal distribution, and that's the density function, okay? And basically the standard normal distribution is basically standardized around 0, okay, or around the mean. And the reference here is Z, which equal X minus mu, that's the true mean, divided by the standard deviation. And these are the standard normal distribution, okay? And we get from this the probability for any Z. Here, the characteristics of the standard normal distribution is basically the mean and the median and the mode. It's a symmetric distribution, first of all, and the mean equal the mode and the median. It's all, there is no skewness. It has 0 skewness, okay? Under the curve, okay, basically at the 0 you have 50% below and 50% above. The area distributed as following, okay, between the mean and two standard deviations. Okay, the area or the probability for 95%, for example, is of all observations are within mu plus or minus 1.96 standard deviation. Okay, see, you know, if you add one standard deviation to the mean here, if you add, that's the mean at the zero standard. If you add one and subtract one, you cover this area, this probability, 34% and 34% added together, that's going to be 38%, which is here, 38.3 of observations are within mu plus or minus one standard deviation. 95% of observations are within, you know, plus or minus 1.96 standard deviations. We'll use this, you know, and, you know, 99.7, that's practically 100%, which is basically this, the mean of the sample plus or minus 3 standard deviation or 3 sigmas. The key we need here is basically what we call standard error. Okay, اللي هو الخطأ المعياري يا شباب. The standard error in the sample is basically the standard deviation divided by the square root for the sample size. That's the standard error. Okay, and the true mean is basically the mean of the sample plus or minus 1 multiply the standard error. That's at degree of confidence 67%. At degree of confidence 95% is going to be 1.96 standard error plus or minus to the, you know, added to the mean. That's basically, we are assuming, okay, that the standard error is normally distributed around the mean of the sample. Okay, having said that, then this becomes true. Then if we know that, if we have this relationship, we can estimate, you know, so in other words, that's the error, this right side, that's the error in the measurements. So if we have a limited size error, okay, we can work it the other way around, okay, and use that to estimate the sample size. فاهمين يا شباب بتكلم في ايه؟ I need someone just to explain to me what we're talking about. Yes, we are having here an example for calculating the standard error. For example, if we have a speed study where we have the mean was 65 kilometers per hour, okay, for the sample. The standard deviation was plus or minus 8 kilometers per hour, and the sample size was 215 observations. Then the standard error becomes the standard deviation divided by the square root for the sample size, which is 8 by square root of 215. That becomes plus or minus 0.5455 kilometers per hour. Then the true mean, and we have here to differentiate between the true mean and the sample mean. The sample mean, as I mentioned, that's the average for your observation. But here the true mean, that's the average for the population. And you didn't measure the population, you just measured the sample. So the true mean becomes what? Becomes X bar plus 1.96 multiply E. Why I'm using 1.96? Because I'm assuming degree of confidence 95% degree of confidence. مفهوم يا شباب؟ يبقى هنا here the mu at this degree of confidence becomes how much? Becomes 65 plus or minus 1.96 في 0.455. What's going on? Then this becomes 65, that's 1.96 multiplied 0.5455. So this is 65 plus or minus 1.07 kilometers per hour. What does this mean? This means that the true mean for the population based on this study, okay, is 63.93 to 66.07. That's the range for the true mean. Or it's 65 plus an error. And the error in this case is 1.07 kilometer per hour, which is actually very good, value, because basically most of the tools that we use for measuring speed by manufacturing, it's within that range. When the error is not acceptable, if this error becomes plus or minus 5, for example, this is not acceptable. Okay, right? مفهوم يا شباب؟ Okay, let's move on to back to the slides. So that's basically the standard error and how we use it to estimate the true mean. Of course, this factor in the example that we discussed early, we were working at degree of confidence 95. If the degree of confidence is 99.5, then we need to multiply the standard error by 3. Okay. Okay. How can we determine the sample size? The sample size, we can determine it, okay, by reversing the procedures that we did before. As I mentioned before, the error is basically, let me shift to the camera. You remember when we said that the mu equal plus error. What was the error? The error can be 1 multiply E. That's if the degree of confidence was 66 or 68%, or can be 1.96 times E. That's if the degree of confidence was 95%, or 3.0 multiply E. That's for 99.75% degree of confidence. Okay? Okay. So if we want to determine the sample size, what can we do? Okay. Let's do this. The error equal, let's take, for example, this case. It's 1.96 multiply E. So if we have a target error that we should not exceed, okay, in this case, what is E? What is E يا شباب? It's standard deviation divided by square root of n. So now n is unknown. We want to determine n. What is the sample size that we have? So we go back, we have error equal 1.96 times standard deviation by square root of n. Okay? Then we can say that square root of n equal 1.96 times standard deviation divided by r. صح? If we square both sides, we end up with the n equal 1.96 multiply standard deviation divided by the error square. This is at 95% degree of confidence. So let's take an example. maximum allowable error in a speed study was set to be plus or minus 2.0 kilometers per hour. If the standard deviation for that site in previous studies was, say, plus or minus 15 kilometers per hour, what would be the sample size, okay, at 95% degree of confidence؟ يا شباب، طيب دي هنحلها ازاي؟ احنا هنقول الايرور equal 1، في الحالة دي احنا بنتكلم على 95%، اوكي، and 99.75% degree of confidence also. يبقى at 95% degree of confidence هنحسب n، يبقى 1.96 multiply standard deviation، اوكي، على that's n على الايرور، this is square، يبقى هنا n equals 1.96 multiply standard deviation how much 15 divided by 2 square how much يا شباب؟
احنا غيرنا بس معادلة الترومين صح؟ خلينا الان هو المجهول.
ومين اللي بيتكلم؟ This one will be 203 that means 204 observations.
دكتور هذه معادلة الترومين؟
دي مش معادلة الترومين، انت عرفت ايه
المفروض؟ خلينا الان هو المجهول.
باشمهندس، المسألة بتقول ايه؟ هنا لو في the maximum allowable error، اقصى ايرور مسموح به في الدراسة عندنا، تمام، هو بلس اور ماينس 2. انا مش عارفين ايه هو الترو مين، انا لو عاوزك تحسب لي الدراسة بتاعتك، تمام، فانت عاوز تحسب هتاخد كام قراءة، تمام، الاستادي بتاعتك هتعمل كام، هتاخد سامبل قد ايه، يعني هتاخد 100 قراءة 50 قراءة، على اي اساس هنحدد on what basis you see. So here we have standard maximum allowable error 2، وعارفين من دراسة سابقة قبل كده ان الستاندرد ديفيشن في الموقع ده بلس اور ماينس 15.
دكتور وائل،
نعم،
طالع عندي 216.
انت عملت 1.96 في 15 divided by 2.
يس.
اوكي،
من وين جبنا ال 15 يا دكتور؟ منين جبنا ال 15؟
مين اللي بيسأل؟
انا فهد.
فهد، ركز معايا يا فهد. 216، sorry I was mistaken. منين جبنا ال 15؟ The 15 either you do a study and get take a sample and get the standard deviation, or it was from previous studies. يعني اتعملت دراسة قبل كده، اوكي، وعارفين احنا عرفنا منها الستاندرد ديفيشن في الموقع ده. واضح؟
ايوه واضح واضح.
ماشي، لان هو دايما الستاندرد ديفيشن decreases when you increase the sample size, does not increase. فهمتني؟
اوكي فهمت. بس القانون هذا هو مركب ما بين قانون الاي والقانون اللي فيه الديجري اوف كونفيدنس.
ماشي، هو مش مسألة قانون degree of confidence. احنا اللي كنا بنقوله ايه؟ ان الترو مين بتساوي ايه؟ اكس بار بلس ايرور.
ايوه
تمام؟ طيب بلس اور ماينس ايرور. الايرور ده عبارة عن ايه؟ الايرور ده بنفترض هنا ان الستاندرد ايرور متوزع accordingly بالنورمال ديستريبيوشن حوالين الميو، صح؟ فهنا لو عاوز اعرف الميو حدوده فين على حسب الديجري اوف كونفيدنس اللي بتكلم فيها. فلو بتكلم ميو تمام ات مثلا 95% كونفيدنس، اوكي، هيساوي ايه؟ هيساوي اكس بار
1 بوينت
بلس اور ماينس 1.96 مضروبه في اي. تمام؟ لو بتكلم ميو at 99.75% confidence هيبقى x bar plus or minus 3.0 في e، لان انا بفترض ان الستاندرد ايرور ده متوزع according لنورمال ديستريبيوشن حوالين المين. واضح؟
اوكي واضح.
جميل. يبقى انا هنا الايرور، يعني هنا بمعنى اخر بقول لك ايه؟ انت السامبل بتاعتك ده المتوسط بتاعها وده الايرور بتاعها. اوكي؟ فلو انا عاوز تجيب لي تجيب لي تعمل سبيد ستادي، بس الايرور عندك يكون ايه؟ بلس اور ماينس 2. تمام؟ يعني انا بقول
مثل ما حدد في السؤال.
زي ما حددت لك في السؤال، قلت لك الماكسيمم
تمام.
ايرور كام؟ بلس اور
2.
ماينس 2، صح؟ معناها انا بقول
اوكي
لك ان ده تمام اللي هو 1.96 مضروبه في اي should be ايه؟ less than or equal to، صح؟ طب خلينا ان جينيريك فورم ده الايرور اهو، صح؟ طب الاي عوض عنها 1.96 في ايه؟ في ستاندرد ديفيشن على سكوير روت
على
لان
الجذر للان.
less than or equal الايرور، صح؟ شيل دي حطها هنا وشيل دي حطها هنا، then we have what 1.96 في standard deviation على الايرور less than or equal square root 2n، صح؟ لو ربعنا الاثنين يبقى ال n should be greater than or equal 1.96 مضروبة في standard deviation على الايرور تربيع. وصلت يا فهد؟
ايوه هذا اللي كنت ابغاه، بس ان الان كيف جت في الطرف
انا
الثاني
بجيبها
بس.
لك اهو، انا معاك للاخر.
الله يعطيك العافيه.
اوكي؟ مفيش اي مشكله.
اوكي.
اوكي؟ طيب نكمل المسائل اللي احنا كنا بنحلها. تمام؟ يبقى هنا ان طلعت معايا 216. طب تعالى نشوف at 99.75% degree of confidence هوصل لكام؟ يبقى هنا n هتساوي 1 مش 1.96 بقى،
لا 3 دكتور.
برافو ماشي اوكي، في اس دي على الايرور تربيع، يعني هتساوي 3 multiply 15 by 2 square. ده this is n1 this is n2. كام يا شباب هيطلع؟
تطلع 506.25.
يعني بنتكلم في 510 observations. لاحظ ان الفرق هنا قد ايه؟ much higher. تمام؟ يزيد اكتر بقى لو عملت ايه؟ لو قلت لك الايرور الستاندرد ايرور بتاعي حصل له ريدكشن، يعني بمعنى اخر قلت لك ايه؟ if مثلا الايرور if the maximum error was plus or minus 1. تعالى شوف لي بقى دول هيبقوا كام. N1 هتبقى كام؟ 1.96 في 15 divided by 1 square، و N2 تساوي 3.0 في 15 divided by 1 square. كام يا شباب هنا؟ دي هتبقى 800 وكام؟
864 865 تقريبا.
865 صح؟
ايوه.
دي هتبقى 2000 وكام؟
2025 2030
2025. لاحظ الارقام زادت ازاي؟ يبقى هنا we must be very careful في allowable error قد ايه. لما انت بتطلب مثلا من مكتب يعمل لك دراسه او تطلب من حد يعمل لك دراسه you have to be reasonable. تمام؟ ليه؟ اول حاجه plus or minus 1 this is not practical standard error في السبيد ستاديز. ليه؟ لان الجهاز اللي انت بتقيس بيه اصلا ده الايرور بتاعه اكتر من كده كمان. يعني السبيد جن that we were using the error the measurement error is plus or minus 1 mile per hour، يعني تقريبا plus or minus 1.6 kilometer per hour. تمام؟ if you are asking for a study that's the error going to be less than the tool you are measuring, that's nonsense. Usually in our case, for example, plus or minus 2 kilometer per hour. That's the minimum you can go. Below this, it's going to be impractical. You're going to just waste time and you are not going to get really a true advantage of that. Okay? مفهوم يا شباب؟ Okay, let's move on. So that was the errors and the sampling. Okay.
دكتور
Yes.
دكتور عذرا عن المقاطعة، احنا متى بنخلص؟
It's an open session. We're
ايوه
gonna finish
دكتور،
when we finish the
لأن
talk.
لأن دكتور عندي بكرة اختبار ومحتاج والله للوقت يا دكتور.
Okay, if you want to stop now, okay, that's up to you. But I'm continuing.
انا
خلاص
دكتور
ما في
وائل
مشكلة،
عندي
لأن هي ريكورد يا دكتور،
Okay,
فإن
hold
شاء الله
on.
ما يضيع شيء.
Okay, now we are done with the sample size and how we are deciding on the sample size. Now we go to another key element, which is the Poisson distribution. We discussed before the normal distribution and how we are using it in the distribution of the error in the samples. Now the Poisson distribution, that's a key distribution that we use in traffic engineering. Poisson distribution is known in traffic engineering as the counting distribution, okay? Because it has the clear physical meaning of several events X occurring in a specified counting interval of duration T, okay? And in a one parameter distribution. يعني هو ده distribution يا شباب one parameter distribution, okay? بيعتمد على events, okay, occurring in period time T. يعني Bx ده ال probability of X occurring, okay, يعني Bx هو probability of X number of events occurring in a time period T. تمام؟ M, that's the average rate of occurrence of events in period T. تمام؟ ناخد مثال على ذلك. if the average number of accidents was 12 accidents per year, okay, what is the probability of one accident per month, okay, two accident per month او zero accidents. يبقى هنا يا شباب في المسألة what is x، هنا ركز بقى معايا كده، x في المطلوب الأول هنا x equal 1، هنا x equal 2، هنا x equal 0. عندنا 3 probabilities. مكتوب هنا what is the probability of 1 accident per month, 2 accident per month. اوكي طيب البارامترز بتاعت الديستريبيوشن بتاعتي، التي بتاعتي هنا كام؟ احنا بنتكلم بير مانث صح؟ لكن عندي هنا الاكسيدنتس بير يير. طب حاجه من الاثنين، يا اما اتكلم ان الاكس، طبعا الاكس بخليها انتجر زي ما هي، بحول الاكسيدنتس بتاعتي من ان هي بير يير تبقى ايه؟ بير مانث. يبقى هقول الام بتاعتي هتساوي 12 بير 12، لان هي كانت 12 اكسيدنتس بير يير صح؟ لكن انا هنا التايم بيريد اللي بتكلم عليها ايه؟ مانث. يبقى هنا ده الام هتتحول ان هي تبقى 1 accident per month. تمام؟ طب هنيجي نحل الكلام ده، هيبقى كالاتي. خليك معايا دي واحده. احنا كان قلنا عندنا ام ايه البروبابيلتي ان يحصل عندي 1 accident per month، 1 accident per month، او كان 4 accidents ولا 3 accidents و 2 accidents per month و 0 accidents per month. تمام؟ وقلنا ان الام بتاعتنا كانت بتساوي 1 accident per month. يبقى ال P of X هتساوي E minus M في M أس X على X فاكتوريال. دي المعادلة بتاعتنا. طيب لو قلنا X بتساوي 1، يبقى probability إن 1 accident per month هتحدث هتساوي كام؟ هتساوي E أس minus 1 في M اللي هي 1 أس 1 على 1 فاكتوريال. هتساوي كام؟ X equal 2، يبقى probability of 2 هتساوي E أس minus 2، E أس minus M سوري، minus 1 في M اللي هي 1 أس 2 على 1 فاكتوريال. طب X equal 0، إيه احتمال إن ما يحصلش أي accidents؟ هتساوي probability of 0 E أس minus 1 M 1 أس 0 على 0 فاكتوريال. حد يحسبهم يا شباب؟
ثواني يا دكتور.
دي هنا 2 فاكتوريال باي ذا واي. دي هنا دي اكس ودي اكس، دي هتبقى بوينت كام؟ بوينت 3 something I think.
كيف تنحل بالحاسبه الاكس تعجب اللي تحت؟
نعم
0.36 يا دكتور.
0.36. طب وهنا تبقى بكام؟ 0.18 صح؟ طب دي هتبقى كام؟ هو دي مش علامة تعجب، دي فاكتوريال. دي العلامة دي x فاكتوريال، معناها x مضروبة في x minus 1 في x minus 2 لغاية ما توصل لواحد.
0.36.
0. كام؟ 36. اوكي، يعني احتمال ان يعدي شهر بدون حوادث 0.36، واحتمال يعدي شهر بحادثه واحده، تمام، 0.36. احتمال يعدي شهر بحادثتين 0.18. طب شوف لي كده احتمال ان يحصل 12 حادثه، ال 12 حادثه في شهر واحد.
Uh, 7.68 ضرب 10 أس -10.
7.68 في 10 أس ناقص 10، يعني تقريبا زيرو. ده إحصائيا يعادل الإيه؟ الزيرو. أوكي يا شباب؟ يبقى ده وده احتمال بعيد جدا، يعني هم في المتوسط on average 12 accidents per year. So it's a very slim, almost zero probability that this can happen in 1 month. أي سؤال تاني يا شباب؟ Okay. This we will conclude the Poisson distribution. There is another issue with Poisson distribution that we need to discuss, which is the time headway application. We use also Poisson distribution for the time headway. Basically, the probability of zero, that's the probability of that headway occurring at that time. And we use this especially to estimate the capacity and at stop signs and this kind of, in the gaps, in determining passing gaps and so on. Okay. Okay. Then that's okay. We stop here. Hold a second. Okay. Now we are going to continue on the traffic stream characteristics, traffic studies, and field assessment. That's basically what we discussed with regarding to the speed studies, volume studies, and travel time studies and delay studies. As we mentioned in the lab, we had the speed study, okay, and we mentioned that usually we conduct spot speed studies, okay. Usually spot speed studies are conducted for a traffic stream where the traffic volume is within 750 to 100 to 1,000 vehicle per hour per lane. For other types of facilities, if the traffic flow is less than 500 vehicle per hour per lane, we can use this speed studies. We don't conduct this speed studies in case of traffic jams or congestion, okay? Must be in a free flow condition or near free flow condition. Speed definition of interest, basically we have the average or time mean speed, standard deviation, 85th percentile speed, and the median speed. These are the key values that we want to get in our study. Okay, the spot speed studies basically is defined as the average speed of vehicles passing a point on a highway, which is basically the time mean speed. The uses of spot speed study data to determine speed limit for applications, to assess speed limit enforcement, to see if people are following the speed limit or not, or we need more further enforcement. We have other specific applications. If, for example, if we want to evaluate the level of service, to have a level of service assessment, we can conduct a spot speed study to assess the free flow speed. For signal timing purposes, okay, in estimating the yellow and or red times, to determine the approach speed, to determine the appropriate side distance, for safety analysis also and accident analysis, we conduct spot speed studies. Methods of measuring speed, we can use the manual method, as we discussed before, by having two marks and measuring using a stopwatch and measuring the time for vehicles to pass this distance, which is not accurate. The most accurate basically is the speed radar. But we mentioned for speed radar that we need to have a correction for the angle of the speed radar. The main disadvantage of the speed radar is basically that it's difficult to conceal, and usually drivers associate the speed radars with police enforcement, and they try to reduce their speed. So this way you might not get an accurate, realistic results for what's going on. As I mentioned, there must be a correction for the Doppler radar results or the speed gun results by dividing by the angle of aiming. The volume is okay. Usually we do a volume reduction, okay, by drawing the histograms and the cumulative frequency, okay, to estimate the 85th percentile, the 50th percentile, and the 15th percentile. Then these are the main descriptive parameters that we need. So we have the graphical representation of the frequency histogram and the cumulative percentile. Then we have the quantitative values. We have the mode, the median, the mean, the standard deviation, the 85th percentile and the 15th percentile speeds. Then we calculate the standard error and the true mean range, okay, at a degree of confidence, usually 95%. Then we can revise this, as we mentioned earlier, to estimate the sample size, okay? Then this another test that we can do for speed size, which is the before and after analysis. That's where we compare two studies together, okay? So we conduct the z-test. In this way, I think we have discussed this before, but we are not going to elaborate on this more today. Okay, volume studies. We have discussed this in the lab, and we are not okay. In the volume studies, we need to be careful in one aspect. We need to first of all know what's volume. Volume is the number of vehicles or person passing a point during a specified time period, which is usually 1 hour, okay, but need not to be more, can be 1 day or month or year. There's the rate of flow, the rate at which vehicles, persons pass point during specified time period. There's the demand, and we need to be careful. Demand is the number of vehicles or persons that desire to travel past a point. So the rate of flow, that's the vehicles that are passing or we observe it passing. But the demand are the number of vehicles that want to pass this point. Capacity is the maximum rate at which vehicles can traverse. That's the maximum flow that can go through a point. That's an example for the volume, demand, and capacity. So we have two approaches, approach 1 and approach 2. The capacity for approach 1 was 4,000. The demand was 3,800. The observed volume will be 3,800. For approach 2, okay, the capacity was 4,000. The demand was 3,600. The observed volume is 6,600. But both volumes, approach 1 and approach 2, merge together in one approach, where this resulting approach, the capacity is 6,000 vehicle per hour. The demand is basically the total demand on approach 1 and approach 2, which is 7,400 vehicle per hour. But the observed is not going to be the 7,400. It's going to be the 6,000 vehicle per hour. Okay. So if the demand exceeds the capacity, the flow rate or the volume will be just the capacity. This, give you an explanation and how the demand, okay, and the capacity and the observed volume works. Okay, the red line is basically the observed volume. The solid line, that's the demand. The dotted line, that's the capacity. Okay, the traffic volume studies, we have first method, that's the counting. Okay, the counting using a tally sheet, which is a piece of paper, and we just we put it in a table, and we mark in terms of 4, then dash, horizontal dash, that's 5. Or we have the mechanical counters like this. Okay, it can be mechanical counting board like this one. This usually we use it for intersections. We have a manual counting board, but electronic, digital. Okay, like this one. Then there is a these are portable counters. The portable counters, it's basically a pneumatic tube counter. Okay, which works. You know, this is for longer than 1 hour. That's for maybe for more than 1 day. Usually we keep it for a week or maybe 2 weeks even. And there's the permanent counters, which is basically like this one. These are inductive loops, and these are placed in strategic locations in the network. And the subject of, or the objective of these loops is to detect flow rate, hourly flow rate, daily flow rate, or flow volume, and the average annual daily flow volume. Also, it can detect speed and the average speed. As you can see, we have 2 loops consecutive in per lane. The permanent counters, these are basically inductive loop detectors. It's a coil, copper coil, you know, placed in the pavement, and it has an induction from the engine block. You know, there's a signal induced, and that's how it detects a vehicle. There's another technology, which is a video imaging technology. Okay, like this one. We can have a virtual loops, okay, and vehicle detection technology. Okay, travel time studies. We are not going to discuss this one here now. Then we have the delay study. Okay, we discussed this in the lab. Okay. Then we move to the capacity and level of service analysis for freeways and multi-lane highways. And I'm going to stop here, and we are going to continue on that at a later time, inshallah. Any questions so far?
It's clear.